Chun Lin. He is an LLM postdoctoral fellow and a PhD candidate in the Health and Clinical Informatics program in DMICE. He received his MD degree with a double major in traditional Chinese medicine at Chang'an University in Taiwan. He received his master's degree in biomedical engineering from Carnegie Mellon University in Pittsburgh. He finished 2 years of medical resident training in Taipei City Hospital and worked as a research associate on a clinical research team for 2 years at the University of Pittsburgh. His current research projects are related to the secondary use of EHR data with machine learning algorithms to improve clinic workflow efficiency and for progression, prediction, and risk assessment of glaucoma with the EHR data. Today, he is defending his dissertation proposal. So Wei Chen, if you'd like to start sharing your screen, and welcome to everyone.
Okay. So can you see the screen and hear my voice?
Yes. Perfect.
Okay, thank you everyone to join today's meeting. I'm going to talk about application of machine learning for glaucoma using EHR data. In the beginning, I would like to thank you all my dissertation advisory committee, Dr. Chen, Dr. Huibar, Dr. Chen, Dr. Song, and everyone in DMICE. The research was funded by National Library of Medicine Training Grant. So the first question is, what is glaucoma? Glaucoma is a group of eye disease characterized by progressive degeneration of optic nerve and the visual field loss that are irreversible. The most common type of glaucoma is open-angle glaucoma. And in our study, we will focus on the open-angle glaucoma. Right side figure shows the structure of glaucoma. So we can see in the glaucoma eye, the outflow of adequate humor was blocked, and it increased the intraocular pressure, and it might damage to the optic nerve. Glaucoma is the second leading cause of blindness in the world. In 2020, the estimation number of glaucoma cases is more than 65 million. And in US, glaucoma affect about 2% patients that older than 40 years old. In the early and middle stage, there are no significant glaucoma. The only symptom we can observe is a slowly progressive visual field decrease. Several eye exams can be used to make diagnosis of glaucoma, include the intraocular pressure test, visual field test, and people use the optic coherence tomography, OCT, to measure the retinal nerve fiber layer thickness. Medication are critical for preventing glaucoma progression. The mechanism of medication are either increase the outflow of adequate humor or decrease adequate humor production. Surgical intervention was used for rapid progression cases or for some patient in response to the medication therapy. Both laser and conventional surgery allow more outflow of adequate humor. The most common conventional surgery is trabeculectomy, and which remove the portion of the trabecular meshwork and increase the outflow of adequate humor. One critical issue of glaucoma is rate of progression. This figure shows 117 eyes of 86 patients, and the y-axis shows the mean deviation. The mean deviation gives an overall value of the total amount visual field loss, with normal value typically within 0 dB to -2 dB. The mean deviation value becomes more negative as the overall visual field worsens. So in this figure, we can show some patient progression was stable, and there's a few patients their progression improved, and some patients shows a rapid progressions. So as shown in the figure, we can find the rate of glaucoma progression is varying among patients. Around 3% to 17% of glaucoma patients show a rapid progression rate. Quickly progression patients are highly risk of blindness and need early intervention. So early identify rapid progression patient is critical to prevent vision loss. However, predict glaucoma progression is not an easy task. Glaucoma is a complex and multifactorial disease. Many factors such as age, gender, family history, and some other eye disease, the baseline eye measure, and many factors can associate with glaucoma progression. So the complexity of disease made it hard to predict disease progression. Machine learning model is a possible way to handle such a high complexity disease progression. And based on the literature review article published last year, there are about 38 studies mainly use structured data and the functional data for glaucoma management. 31 studies focus on improving diagnosis, and only 7 studies focus on prediction of progression based on structure or functional data. In addition, based on our literature review article, we explore the application of AI technique with EHR for eye disease. There are only 2 studies use the machine learning model with EHR for the glaucoma management. The first study predicting the need for surgical intervention, and the second study developed a glaucoma phenotype based on EHR data, and this phenotype was used to improve the predictive performance of image-based classifier. Based on this review, we found that most studies focus on improving diagnosis. That's easy to understand since they are lacking a gold standard tool for glaucoma diagnosis. So many studies try to find some way to improvement the diagnosis. And the fewer studies focus on the glaucoma progression prediction, and most the prediction model based on single measure like visual field or retinal fiber layer thickness. However, use single measurement like visual field change to operationalize rapid glaucoma progression may not be comprehensive enough. Some clinical feature like optic desk hemorrhage can be indicator for rapid progression cases. In addition, there are some data issues. Most studies use image data, and there are only 2 studies, as we show in previous slide, use the EHR data, and they only use structured EHR data. However, some important features like patient's medication adherence are recorded in free text data like progress note. Otherwise, time series data like the eye exam result may not be complete for many glaucoma patients. For example, the no observed or missing data of visual field are common issues since the patient may not receive the visual field exam for every visit. So that's how to get a comprehensive data and accurately predict rapid progression patient. It's a challenge work. Here lists the possible feature for glaucoma progression from EHR data include structured data like eye exams, patients' demographic data, patient medical history, and their family history, and also contain the unstructured data like glaucoma medication and medication adherence. So we figure out several challenges for using EHR data in predictive model for glaucoma. Such as some important information and feature was recorded in the unstructured data like progress node, and time series data like eye measurement contain some unobserved or missing data, and use single eye measurement to trace the disease progression may not be comprehensive enough. So for our study, there are 2 specific ends. In specific end 1, we try to address the challenge for the secondary use of EHR data for the prediction model. We use the natural language processing method to extract feature from unstructured data, and we will use several analytic methods for managing missing data problem. And we will overridization outcome measure from rapid disease progression. In specific N2, we will develop prediction model for rapid glaucoma progression by exploring multiple machine learning methods. We will not only focus on the single binary outcome, but also explore the prediction for multi-label classification outcome. And we also want to identify possible factor for rapid glaucoma progression. So in the M1A, we will use natural language processing to extract features from unstructured data. As shown before, medication therapy are crucial for prevent glaucoma progression, and which is important to get correct medication information. However, extract medication information from EHR data is not so easy because sometimes medication list is inaccurate. Since some medication, some prescribed take by other place like CVS, and this change may not be reflected in the medication list, and sometimes that already expired medication still can see in the medication list. And we'll assume that progress note contain more accurate record because physician will record a patient's medication change or new medication for each visit. The right side figure shows two examples of medication information mismatch. The left side shows the mismatch of medication list and the medication in progress note. And right side shows there some medication information recorded in the progress note, but for this visit, there's no medication list information. Here is an example of medication mismatch. In summary, there are two medications are the same with different route, shown as red, and the blue color shows the medication was recorded as brand name in progress note, but actually it's the same drug in the medication list. And there are three medications different between the medication and the progress note. So the first part of N1A, we will extract medication information from progress note and check the medication list accuracy. There are two steps for this part. The step one, we manually review 150 glaucoma patients' progress note and their medication list. And in the step two, we will use natural language process to automatically extract medication information from progress note and make the comparison with medication list. In the step one, the patient's most recent office visit will be manually reviewed, and any medication mismatch or discrepancy between the medication list and the progress note would be labeled. Because we have three reviewers, so we do the cross-validation to verify the review process with 20 random sample notes. After validating the review process, another 130 progress node was selected by stratified sampling method. Here is a result of the step one. So because we still working on another 40 progress nodes, so here is just the result for the 110 samples. So we can see there are around 30% medication mismatch was found in this 110 samples, and more than half progress node contains at least one mismatch. So here we can see the perfect match medication list and the progress node is 46%. After figure out there's some problem of the medication list and the medication information in the progress node, in the next step we try to develop a natural language processing model to extract the information from progress node and make comparison to check the medication list. Since manually review this chart and medication list is really spend a lot of time and time consuming. We use the named entity recognition model to do this work. Named entity recognition model, NER, is a subtask of natural language processing that seeks and categorize specific non-entity in the body of text. We use the SpaceC library. SpaceC is an open source library for advanced natural language processing in Python. We trained the NER model with 7 NaN entities, including drug names, route, frequency, dosage, strength, duration, and current drug use term. The current drug use term is some words that indicating the patient is taking some drug or stop using some drug. For example, some words like continuous, discontinuous, or stop, like current ocular mass, some specific term that recognize the patient is taking or stop the drug. So we add this NaN entity with other drug information to get more accurate medication usage information. More than 1,800 sentences were annotated, and these sentences were split into training data with 75% and the testing data with 25%. The bottom figure shows some example of the NaN entity. The green color shows the drug NaN, and here is strength, and the red shows the dosage, here's the route, and orange is frequency. So that's the example of NaN annotated sentences. The figure shows the architecture of the NER model. So the sentences was extract from the progress node, and we use a browser-based annotation tool, WebAnno, to annotate the sentences. And the annotated sentence was split to training and testing data, and training data was used to train the SpaceC NER model. We used the empty English model with NER pipeline, and the trained model was verified the testing data and used to extract the medication information from the progress node from other samples. Here is the result of NER model with different proportions of training data. We can see the largest sentences. We have acceptable accuracy with F1 score equal to 92% for the drug, and the frequency and the route is better than the drug accuracy. Here is our preliminary work, and we're still working on annotate more sentences with different form and turning the prediction model to improve the model performance. And we will use this NER model to extract the medication information and develop a tool to check the medication list accuracy automatically. Other than medication information, some other features is also important for the glaucoma progression, like medication adherence. Medication adherence is critical for preventing the disease progression, and studies suggest that non-adherence in patients with glaucoma has been reported up to 59%. And several factors can affect the glaucoma medication adherence. For example, some eye drop is painful, so it's make difficulty for patient continue use these eye drops. And as mentioned before, in the early and the middle stage, the glaucoma symptom is not clear, not significant glaucoma symptoms. So some patients just lack of motivation, and for some senior patients, they may just forget to take the drug. And so the medication adherence is pretty common issue for the glaucoma patient, and need to extract this information from the progress node for a prediction model. In addition, some clinical feature can represent the rapid disease progression. Like glaucoma patients with optic disc hemorrhage are likely to show faster progression rate. but they're similar to the medication adherence information. There are no specific structured data we can easily to access. There's no like specific code or some table or sheet that we can directly extract. So we need to find some way to get this information from the unstructured data like a progress note. We plan to use text classification tool to extract desk hemorrhage and medication adherence information from the progress note for glaucoma patient. Text classification is the process of categorizing text according to its content, which is a subtask of natural language processing. This figure shows the basic architecture of the text classification model. So we need to extract some progress node and give the label for the node and the training model to classify the node with different label. Here is the possible steps that we can handle this model. So we will manually review 400 glaucoma patients progress node and labeled node with medication adherence or non-adherence or contain desk hemorrhage information. And the text in the node will transfer to the numeric vector, and this training data will be used with the supervised machine learning like support machine or deep learning model like a convolutional neural network to classify the nodes. The model will be evaluated with precise recall and affirmation, and the trended model will be used to classify the other progress node to extract the feature for the prediction model. And in the specific M1B, we will use different analytic methods for managing missing data, missing time series data problem. Glaucoma patients' eye exam result may contain many missing data or unobserved data, especially for like OCT result or eye visual field test. Since patients may not receive all eye exam every visit, for example, patients glaucoma patients routinely have at least 2 office visits per year for the glaucoma management, and for some severe symptom or rapid progress cases, they need more frequency office visit. And for each visit, the patient's intraocular pressure, visual acuity, CD ratio were recorded, but some eye measurement like visual field measurement, OCT result, just scheduled for the once per year. But for some cases that can be more often, but it's just a roughly number. But this difference leading to some unobserved or the missing data for the visit follow-up visit data set. And sometimes data recall every visit can be missing or unusable. So all this problem lead the missing data issue for the eye exam data set. So we will use the classical statistic imputation method to handle this problem. There are two possible ways or that we can use for handle this issue, include forward filling and linear filling. Forward filling involves replacing the missing data using the last time point data, and the linear filling uses the linear interpolation between the previous time data and the next time point data. In addition, we also plan to use some machine learning model to predict the missing data to replace it. We can use the Bayesian model or random forest. And as we create a time series data set for the eye exams, we can try to use the recurrent neural network to handle the missing data issue. Recurrent neural network is a subtype of deep learning and which is good to handle the time series problem. which can learn the information from previous prediction and remember the information from prior input throughout the time step in the training process. As shown in the figure, the left side shows the traditional forward network and right side shows the recurrent neural network. One of the main difference in this model is how the input data is taken. In traditional model, which takes the fixed amount of input data all at the same time and produce a fixed amount of output each time. And our recurrent neural network is in contrast. It takes the input data at part as once, and the input data is intake as a sequence. So we can see in the the time one input data, the first time step data will input the first cell and get the output, and the output one will transmit to the next cell and so on. So we can use this model structure to handle the missing data for time series data set. The input data set is different between the traditional prediction model and the recurrent neural network. In traditional prediction models, the input data format in 2 dimensions, but for recurrent neural network, the input is 3 dimensions. So in our study, the first level is each eye of patient, and second level is each visit, and the third dimension is the eye measurement for each visit. In the N1C, we will define the outcome features of the rapid progression glaucoma. Here is a list of predictors and outcome features we already extract and we plan to extract. In the predictive features that contains several eye measurements and some patients' demographic information, including the insurance status and their race and zip code. Also, some clinical history, including family history, smoking history, and several data that extract from the unstructured data, like medication usage and medication adherence. And we use 3 outcome features to define the rapid progression glaucoma. The first one is annual visual field loss that's larger than 1.5 dB per year. This feature will convert to the binary variable, and the patient receive the glaucoma surgery and the patient present the optic disc hemorrhage is another 2 outcome that used to define rapid progression. The figure shows the calculation example of annual visual field loss. The rate of change of visual field is expressed in dB per year and is derived by the amount change in the mean deviation that happened over the target period of time. So this figure here shows the time change is 1 year and the change is 1.9. So the slope is 1.9 dB per year. So after extract the data and handle some missing data problem, the next step in the specific N2, we will develop prediction model for rapid glaucoma progression. Here is the graphical overview of our specific N2. We handle some missing data problem and get data in the N1. And after do some data preprocessing work, we will develop several prediction model for both single output and multi-label output. For single output, we plan to use linear regression, support vector machine, random forest, gradient boosting machine, and XGBoost to develop the prediction model. And for the multi-label output, we plan to use classifier chains and the deep learning like multi-layer perceptron model to handle this multi-label classification problem. The model will be evaluated with several metrics. For the single output, we will use the accuracy, AUC, precision, recall, F1 score. And for the multi-label classification model, we will use the micro and the macro averaging with the metric like AUC score, and also use other metrics like a Hamming loss metrics and exact match ratio to evaluate the multi-label classification model. The feature importance will be calculated with each model and used to explore the possible risk factor related to the rapid progression. So overall, the output of the model will be the feature importance based on each model and based on all model, and the output of the prediction model with for single output and the multiple label classification output. We also evaluate the imputation method's performance with the prediction model accuracy. So here is the machine learning model we plan to use for the single binary output, include a logistic regression, support vector machine, random forest, gradient boosting machine, and XGBoost. Here is the basic idea about these machine learning models. Logistic regression is an extension of linear regression, which with the sigmoid function convert the output from the continuous variable to the binary outcome. And the support vector machine is another popular use of machine learning model with a hyperplane created to split input data into two distinct groups and can be used to classify new data into similar distinct categories. The random forest attribute and the gradient boost machine is ensemble method with decision trees. The enhanced bagging method and boosting method was used with the decision tree and improved the performance of the model. Here is several evaluation metrics we plan to use for the single output models, include accuracy, precision, recall, F-score, and AUC score. The accuracy was the method to determine how correct the value are predicted, and the precision determine the reproducibility of the measurement, or in other words, it showed how many of the predictions were correct, and recall shows how many of the correct results were found. And the F1 score is the measurement method that combination with precision and the recall, and it's pretty good for imbalanced data set prediction. And we also use the AUC score to evaluate the model ability to distinguish the different categories. We also plan to develop the prediction model for multi-label classification. The first model we plan to use is classifier chance model. In a classifier chance, the output of one response variable for a subclassifier will be used as an extra feature in the next subclassifier. These additional features allow each chain to explore the correlation among the classes. So as shown in the figure, the output of first subclassifier is C1, and the C1 will use as a training set for the second classifier. And the second classifier get output as C2, and the C2 plus C1 will use with the training set for the for the third classifier. And the order of the in our study we have three outputs, and the order of this output will change to test the best performance order and with different machine learning models. Also, we want to use some deep learning method to handle this multi-class problem. Deep learning neural network natively support multi-label classification problems. which can support by specifying the number of target label there is in the problem as the number of nodes in the output layer. For example, in our study, we have three output: any visual field loss, glaucoma surgery, and optic disc hemorrhage. And we will require a neural network output layer as here with three nodes to handle this problem. The evaluation matrix is for the multi-label classification is a little different from the single output. We will use the Hamming loss matrix and exact match ratio. Hamming loss is the fraction of the labels that are incorrectly predicted, or we can say it's the fraction of the wrong label to the total number of label. In contrast, exact match ratio is which indicating the percentage of samples that have all their label classified correctly. And we will use the micro averaging and the macro averaging with the evaluation matrix for the single output. In micro averaging, all true positive, true negative, false positive, and false negative for each class are summed up, and then the average is taken for the micro averaging. And the macro averaging is more straightforward. It's just take the average of the all measure of the system. And we also want to identify the possible factor for predicting rapid glaucoma progression. As shown in previous slide, in the supervised machine learning model, we will rank the importance based on each model. And the feature importance can be used for identify the possible factors that related to the disease progression. In addition, we will try to use unsupervised learning to identify cluster within the data set. So that means we will set the certain number of cluster of our data set, and this cluster can be a glaucoma phenotype. And we can explore the risk factor within each phenotype to explore the potential risk factor associated with the rapid glaucoma progression. So in our study, in the N1, we will try to address the challenge for the secondary use of EHR data for the glaucoma progression prediction model. We use the natural language model to extract the medication information and check the medication list accuracy. And we plan to use other NLP method to extract the medication adherence and other clinical feature. And we will use analytic method to manage the missing time series data problem and define the rapid progression with three different variables. And in the N2, we will develop the prediction model for rapid glaucoma progression with several machine learning models. And we will focus on both single output and multi-label classification output. And we will try to identify possible factor with supervised and unsupervised machine learning models. Thank you for your attention, and all questions are welcome.
Thank you, Wei Chun. Very nice job. Would like to open it for questions from anyone. Okay, I have a question. Could you describe the data set that you will be using for both AIM-1 and AIM-2, sort of like, you know, who the patients are, what the time period is, about how many patients or eyes are in the data set?
Currently, we extract the patient with glaucoma diagnosis both in the glaucoma specialty and other specialties from 2013, and we extend 2 years before 2013. And during that period, we have around 6,000 patients with a lot of different eye measurement and demographic data. But some we're still working on extract the like visual field and OCT result because the iProc system was installed after 2017. So before that time period, that we need to find some way to extract more data before 2017.
Okay, thank you.
Yeah, I've got a question.
Okay.
Hello. Yeah, this is Homer Chin. Very interesting work. You know, one question I have is, are you planning to use a data set to build the model and then a separate data set to evaluate it, or how are you going to evaluate it?
Yeah, the data set, when we create a data set, we will split to the testing data and training data and use cross validation method to make sure that the training data is not overfitting.
I'm sorry, how are you going to do that? You're going to use a training data set and then a separate data set?
Oh no, we created the same data set and just split to the training data and testing data. So we will verify with the testing data, and testing data will not leak it to the training model.
You're going to use the same data set for both the training and testing?
Yeah.
Well, if you're training using a data set, then de facto it's going to be pretty good for testing, but it could be an overfit.
Yeah, so we might use the cross validation, like tenfold cross validation, or bootstrapping method to try to get the confidence of the prediction model and decrease the overfitting problem.
All right.
I can just chime in there. I think that'll be a very good idea to do that sort of cross validation, because I think you'll find with especially with the RNNs and the larger models that overfitting will happen for sure.
Yeah.
Any other questions or comments?
Just a very, very cool data set and a really good preliminary project here. So this is really exciting.
Thank you.
Yeah, thanks for showing it.
Okay, well, if there aren't any more questions or comments, then everyone except the dissertation advisory committee is free to leave, and those of us in the committee will remain in Chun.